A previous video, with the link down below, looked into the meaning of the number of moles in terms of thermodynamics in terms of a single component phase equilibrium with two phases, alpha and beta, where since you had equilibrium, the Gibbs free energy was equal to 0, the potential of alpha and beta were equal, and the Clapeyron equation was therefore developed to control all equilibrium, where the change in enthalpy of the transition over T dt is equal to the delta V of the transition times dP. Now let's move on to a multi-component system, meaning I have a solution, where a solution is essentially nothing more than a homogeneous mixture. For the purposes of the rest of these videos and our discussions, component A will be the solvent and component B will be the solute. From general chemistry, you know the vapor pressure of a solution is controlled by Raoult's law, where the pressure of the solution is equal to the mole fraction of A times the pressure of the pure solvent A. If I look at a distillation, the distilling pot is going to have a preponderance of A since it's the solvent. The mole fraction of A in the pot is going to be much larger than the mole fraction of B. However, in the gas phase, B has a much higher vapor pressure in the pure state. So what will occur when I do the distillation? In the receiving pot, the fraction of B will be much higher than it was initially, and the fraction of A will be much lower than it was initially, where the italic Y is used to distinguish the mole fraction in the gas phase. Total pressure of the system will simply be equal to P of A plus P of B. But there are two ways to derive this. First of all, the pressure of A plus B would be the fraction of A in the gas phase times the total pressure, plus the fraction of B in the gas phase times the total pressure. That arises from Dalton's law of partial pressures and governs the behavior of the gas phase. However, since I have a liquid-vapor equilibrium, this will also be equal to the Raoult's law solution, the mole fraction of A in the liquid phase times the pressure of pure A, plus the mole fraction of B in the liquid phase times pure B. This is the first example of thermodynamics of a heterogeneous system with multiple phases. For other examples, we delve back into the chemical potential, which, if you recall, the potential mu of I is the effect that changing the moles of I has on the total free energy of the system at a constant temperature and pressure. In other words, the Gibbs free energy is just the sum of the individual potentials of all the components. Since the potential is related to the Gibbs free energy, the chemical potential of some component A is going to be minus S of A dt plus V of A dP. Since I have more than one component here, I have several different aspects of the potential to look at. There's mu star of A, which is the chemical potential of the pure solvent at whatever condition you're talking about in temperature and pressure. Mu 0 of A, the chemical potential of the solvent under the standard state, and mu of A in the mixture, the potential of A in solution. We're recalling the standard state means 20 degrees C. Every component is at 1 atmosphere pressure or 1 molar concentration. So at equilibrium, you have, by definition, a reversible process that is isothermal, for the simple reason that equilibrium occurs at only one temperature. So the chemical potential of A is simply going to be V of A dP, or RT log P2 over P1. Compared to the standard state, getting A to the state it's in from the standard state, delta mu of A, is going to be mu 0 of A plus RT log P of A over P0 of A. Since by definition the standard state is 1 atmosphere, you get the delta mu is equal to the standard chemical potential plus RT log of P. So for the pure material, mu star would be standard mu of A plus RT log P star. And for the potential of the solvent in the mixture, it's going to be the standard potential plus RT log of P of A in the mixture. When forming a mixture, the change in potential of the solvent is going to be like any other delta, final minus initial. The potential of the solvent in the mixture minus the chemical potential of the solvent in the pure state. Expanding that out, the potential of the solvent in the mixture is the standard potential of the solvent plus RT times the log of the vapor pressure of A in the mixture minus the pure state, which would be the standard state, plus RT log P star. Straighten this out. The change in potential energy to form the mixture is RT times the log of the vapor pressure of the solution over the vapor pressure of the pure solvent. That term, according to Raoult's law, gives you the mole fraction. So the change in potential for the solvent in forming a solution is RT times the log of the mole fraction of solvent in the solution. This actually has a profound effect in explaining why solutions form. By definition, if one has a mixture, the mole fraction of each component must be less than 1. The log of any number less than 1 is going to be negative. So you have a delta A of the mixture being less than 0. So solutions form because they are more stable than either component left to the pure state. The consequences of this on the physical behavior of solutions will be examined in a video that is linked below. Thank you again, and I hope this was useful.